showing last time and I'm again showing here. In particular, you notice that if you are computing just this particular layer first, you have error here. Using that error, you need to change these weights first. Okay? And in doing so, basically actually the way you'll wind up doing is when the sum is over the no, basically you're talking about the error here. Again, I'm taking not cross entropy loss, but rather the squared loss currently. If you keep thinking, okay, the theory is given for squared loss and you're asking everything is, you're saying everything that works is using cross entropy loss, the one after this I will tell you that nobody actually does this differentiation. This is just to show that it can be done once. Okay, we'll show that that's the point about auto-diff. It turns out that everything essentially is done automatically in the backward pass in the current systems like TensorFlow that you have. Okay, they essentially do this gradient propagation themselves. And so you can put pretty much any analytically defined function for which you know the differentials, and then they will then compose the differentials correctly. I'll get to that in a minute. So for now, just see that if you are thinking only in terms of the mean squared error, you will still see that if you go through the steps, the weight update is input size for the weight update for the jth weight is the input AJ. Notice that the AJ is the input for it because this guy is only getting inputs from the interior nodes. The nice thing is for the example that you are looking at, you know what the AJs are. Because given the weights, you know what the AJs are. Do people see what I just said? Right? Because I will put some numbers here. And they're all weights. Because of these weights, I know the numbers in the next level. And then there are numbers there, and because of those weights, I'll get the last number. So everything is actual numerals, even though we're talking in terms of variables. But these numerals are changing. These particular values are changing, step by step by step. That's the thing that you want to get your mind around. And the way they change is they change in proportional to the input and the gradient, which is pretty much what we were talking about earlier, where the gradient here, Wi, is actually just, we've said that this part has been said to be delta. So you threw in the G dash I into the mix, and you call that delta I. And then if you go through the steps for the next one, you continue doing the same thing in terms of chain rule application. Then after some more chain rule applications, you will get to a point where you will see that the way to change Wkj, the weight here, is going to be in terms of using the input for it is Ak times again this gradient delta J, which is coming from these parts. It's essentially again, by this time, notice that you are no longer specifically asking yourself what is the error supposed to be in the interior layer. The way psychologists would ask themselves. Okay? The interesting thing also is that essentially this delta I was the original error in the first level, approximately. And so what you did is you're multiplying it with the weight, which is essentially apportioning the error proportional to the weight, which is exactly what we said psychologists were hoping. Okay? Now, so essentially the gradients basically always look like the input times, the error terms always look like input times the gradient. Okay? And the gradients are being computed step by step. And two things now, which I want to just reduce, let's just see this, to get people to kind of have a sense of this, I would suggest you guys look at this particular page because this goes through excruciating detail doing the forward and backward steps for one network. In particular, I'll just walk you through this so that you will again go through this. I'm not going to say the numbers aloud, but so they take this network, okay? And they will initialize the weights to something because you have to start with some initialized weights. That's what happens all the time, okay? And then they will also start with some input. This particular case, the input is 0.5 and 0.10, 0.1. And they know that the true outputs are supposed to be the true outputs are supposed to be, so if you put this 0.5 and 0.1, I believe if you go through these, and in fact these networks, the weights, the units always are all having sigmoid functions. And so in the forward pass, they will tell you how they computed the activation value coming in. And then they will throw that into the sigmoid function to get the activation coming out. Okay? And then they'll do all these steps. This is basically what computers are good at, and you are extremely bad at it. But you want to do it once just to know that there is no magic. And after that, you just depend on TensorFlow so that you don't have to worry about it. Okay? Okay, so and then you continue, and then you are computing the output for output for O1, which turned out to be 0.75. But remember, it was supposed to be 0.01. So there is an error. Okay? And similarly, you compute, in fact, this is a case where this is a multi-layer, multi-output network. You can do any of these, right? I mean, you can do multi-layer output network. And there are multiple outputs, then you try to minimize the error over all the outputs at the same time. Okay? So you compute the value for this guy O2. O2 is supposed to be 0.9. After he goes through all his numbers, he finds that it actually is coming into 0.77. And then he computes the error, and that takes the error squared, and then essentially passes through these things, passes them back through using the chain rule and using the differentials, step by step by step. Okay? And then if you have to go through the whole thing, and so basically here, for example, he's just putting together one derivative in terms of the multiplication of the chain of derivatives. This stuff you will understand because you know chain rule. Okay? And then you continue, and at some point of time, at the end of the, so basically you have to go through all the layers. Okay? At some point of time, you would have updated all the weights, and so when you have updated all the weights, then you will find that the error, which used to be 0.298371109, is now only 0.291027924. Do you see what I'm saying? Do you think, I wasted my whole day doing this? You're not supposed to do this. Computers are meant to do this. You see what I'm saying? You should do it once in your life just to know that this is what is done. But you are not supposed to be doing this. Doing this for neural networks is like doing differentials by actually computing the limit h tends to 0, fx plus h minus fx by h. You should know that if everything else fails, that's the way to do it. If you are on desert and you have no TensorFlow and you should recognize a cat, you can very quickly do this by hand. Okay, that's basically what this is for. Okay, now here is the thing. So I would suggest that you go through this. Walking you through this step by step will basically put all of us, the rest of us to sleep. Already some people are asleep, but the rest of us also will be asleep. Right? Let's not do that. So I gave the connection basically at the top, and then you can go over that. Okay. So that's basically, that's that network that we looked at, and as he says, it reduces so little. So the thing is, this is actually a network with only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 weights. Just 10 weights. It's a 10-dimensional optimization problem. You know GPT-2, people may have heard of this OpenAI's GPT-2. It has 1 billion weights. 1 billion weights. And all these 1 billion weights are being updated little once, little again, little again. And all your hope is that the theory works and somehow you will reach some reasonable local mean. You see what I'm saying? And because this is basically gradient descent in multidimensional space. Okay, and in general, it's kind of hard to believe that these things work at all. And I find that it's useful to sort of understand that really small steps, as long as they're in approximately the right direction statistically, can lead to pretty impressive outcomes. How many of you have heard of barrier reef? Okay, right? I mean, you have heard of coral reefs in general. Do you know how coral reefs are formed? So Disney goes and slowly builds coral reefs everywhere, right? Coral reefs are essentially the poop of this little aquatic creature. That's like, you can't even see. The plankton, right? And enough of that poop, given deep time, gets you barrier reef. Enough of little step, given enough number of updates, can get you a neural network that actually converges to something reasonable. The only thing going for neural networks as against barrier reef is we can speed up time for neural networks. We unfortunately cannot speed up time for barrier reef. The stuff that we people have destroyed is gone. Actually, I destroyed, you won't see it. Right? So, so that's really the thing. So these are small steps as long as they're in the statistically right direction. And the thing that's like bothersome about anybody who says they pretty much understand why the gradient descent works, probably don't understand what they're talking about. Okay? Because it can only be understood at a certain level of abstraction with the background in statistics. In particular, you remember we actually mentioned, let me see if I can get there. Actually get there later. But in particular, it turns out that you can compute the error here, in this error. Suppose I have been given 1,000 input examples and their labels. That's the training data. I can compute the error run all the 1,000 examples through this network, compute the error for each of the examples, sum all those errors, minimize that. So in one fell swoop, you are essentially doing full gradient descent on the full error. Normally when people think of gradient descent before neural networks, that's what people thought of. You do all your training data, you throw them, you find the output, you compute the full training error. So when I was showing you those TensorFlow videos, the loss that they were showing, that's the full training error and the full test error. So one way of doing this would be to compute the full training error in each step, modify the weights, throw the inputs, the entire training data through the network again, re-update the weights, modify the steps, re-update the weights. That's one way. The other extreme way is for each example, update the weights, which is what we showed here. The first one is called batch or normal gradient descent. The last one is called stochastic gradient descent. In particular, if you have data that is mislabeled, like for example, in the end, some of you who should be getting A plus might be getting D minus. It's just an error. I'll just say sorry, and to myself, not to you. But, and some of you who should have gotten D plus might get A plus. These are errors in the training data. Do you see what I'm saying? And if these errors, if I use those examples, those wrong examples to change the weights, then at that particular point, the weights have actually gone in the wrong direction. Do you understand what I just said? So if I took I mean, I don't know. I mean, some of the grades were actually wrongly given. That's not what I meant to. As the teacher, I gave the wrong grade. So the training examples can be noisy in their labels. And if you just take the individual examples and pass them through, the change may well be in the wrong direction. Because the network says, oh, this kind of bozo should be getting A+. That's not what I meant. That's why, by mistake, that particular bozo got A+. Okay? But if I took all the class, given that I still have a job, it must mean that mostly I do the right thing. In the entire class, I basically mostly the right people get the right grades. But there will be some noise. So this kind of noisiness would be reduced if you took the entire batch of training data and pushed it through the network, computed the error, and used that to change the weights. Do people see this? Right? So you would think, which one do you think would be a better idea in terms of conversion? If you just didn't hear anything else, which would you have thought would be a better idea? Batch. Not batch norm. Don't say the word batch norm. It's a batch gradient descent. First of all, you say that word okay. But batch gradient descent. By the way, batch gradient descent has nothing to do with batch norm. It has the word batch common, just like neural networks have the word neural common in the brain. Okay, so you would think that we should do batch gradient descent. Originally, neural networks people did not do batch gradient descent because if you have 10 million training examples, they never actually had 10 million training examples. They had 1,000 training examples in the old days. Computing one pass was taking too long. And you feel as if, it's nicer to make more passes and hope for the best. And so they would actually try to do, the 1,000 would be split into small batches. 100, 100, 100. And then throw each 100 through the network. Compute the full error for that batch, that mini batch, and then use that to change the weights. You see what I'm saying? That would be called mini batch gradient descent. And the most laziest mini batch is every example, I just throw it to the gradient descent. That is the stochastic gradient descent. Now let me ask the following question. When we got into these sordid affairs, we went from reinforcement learning, right, to learn the value functions. There, what would have made best sense? The batch gradient descent, mini batch gradient descent, or the stochastic gradient descent? Because you can call it online gradient descent, and then it becomes nice. You see, because if you're only getting one example per day, and you still have to learn, you can't say, I'll wait, those of you who say, let me wait until PhD is over and then I'll start answering exams. That's a reasonable thing to do, because after the end of PhD, you'll get some idea how to answer any exam. And so then you quickly go through first grade, second grade, third grade, fourth grade exams, etc., and you're done. Right? We are forcing you to take the first grade exam in first grade. You see what I'm saying? This is because we are saying it's an online world. We basically will get you data one at a time, and then you just have to learn from that data that you have. So the stochastic gradient descent, when seen as online gradient descent, is a great idea. But you also know that stochastic gradient descent will be making moves in arbitrary directions, even though it's supposed to go in a particular direction. So if in fact the right direction towards the minimum is, let's say, this, stochastic gradient descent will be going all over the place, but in general towards the right direction. Statistically speaking, towards the right direction. So if anybody says, I understand this is what it meant, they have no idea. Because in particular, imagine that particular example that I showed you, if in fact this example was wrongly labeled, then you just change the weights in the wrong direction. So the error may be good for this example, but on the entire batch it would be higher. But on the whole, if you do this stochastic gradient descent, it will still work. Okay? Yes?
So in general we can say that batch gradient descent always works better than stochastic gradient descent.
Again, it's a question of No, again, there is no in general and there is no always. We are in engineering world from now onwards, right? You understand the advantages of each of them. Sometimes you have to do online. Sometimes you may want to, that because of which you can do stochastic gradient descent. But in general, actually, there are some interesting theoretical results. People thought that they're doing SGD because they're forced to do it. That the right thing would have been to do the batch gradient descent. But there is enough work that shows that when you can do both, doing stochastic gradient descent actually works fine. In fact, better for very high dimensional problems. Is there a theory? Not so much. Okay? Okay, so if you like that thing, then the other thing you can do, I mean, that was actually a useful thing, and this is also kind of useful maybe for 4 minutes or 5, I think they're each 12-minute videos. I mean, neural networks have become big enough that even 3 blue, 1 brown guy has made them, and it's very useful videos to watch. It actually has nice animations and stuff. This stuff obviously doesn't have animations. You'll have to, sit with your calculator and press. Whereas this looks as if all the numbers are being done automatically. Now, if you're into this, then you don't even need this. Essentially, understanding how anything works is for the birds. Really, when you get into the company, you just have to ask, where is the switch? I put on the switch, and then things will happen magically. Okay? And so, really, the way this backpropagation is done most of the time is this auto differentiation example. Let's see where often. Okay. Yeah. So, the idea is to basically say that you can compute the error numerically, the gradient numerically, just step by step. Okay? And this is what we are good at as computer scientists. So, I want to show, first of all, I want to basically make the point that a neural network, understand this, a neural network, by the way, these are, as I very carefully pointed out, is Andres Karpathy's slides. And so, this part is mine, unfortunately. The neural net is just a huge composed function, right, of inputs. So, Fn of inputs is given to Fn minus 1, is given to Fn minus 2, etc., all the way to F1. You remember the composition of functions. Chain rule is made for composition of functions. Do you see what I'm saying? Sitting there and trying to think of how to deal with an entire composition of functions is painful. Programs are extremely good at doing that. Subroutine calls another subroutine, calls another subroutine, calls another subroutine. I mean, you are just done. In particular, if the subroutines have very regular structure, in fact, this is the only place computer science is actually helping, essentially, because the programming people are helping. Because what happens is that you can compute any arbitrary differential brute force, not brute force, I mean automatically. Okay? In particular, let's say, and I'll illustrate that basically by just taking one function, which itself is a composition of many functions. And then you see how it works, then you realize that that's how basically backpropagation part works in neural networks, in TensorFlow, etc. So they have one forward pass, and then in fact, you don't even have to, once you give the forward pass, they will know what to do in the backward pass. And so none of you actually, this is what I was saying, the reason high school students can do neural networks, even before even knowing what is calculus, is because they don't need to know calculus. Neither do you. Okay? So anyway, in this particular case, right, so I'm considering, let me just go through this quickly and to see, and you can go through this slowly. In particular, this is available also, a written version of this is available in this set of notes that Andres Karpathy has, and it basically goes through the example that I have somewhere here. Yeah, that one. Okay, so I will go through it once just to get you bearings, and then you can spend more time looking at it. So all we are saying is this big function, this function, which looks like a big function, and which looks like a small function to us, can really be written in terms of this flow graph. This is called a computational graph. Right? So you're basically computing this function. what you're doing is you're starting with the weights, and then there are the inputs in green, and then they are being multiplied, so that the inputs and weights are being multiplied, and then you get something here, and then they're being added. So here what's happening is the inside of this is being computed by this part. W0x0 plus W1x1 plus W2. Okay? And then at that point, essentially, you're adding a 1 to that, and then you are multiplying this whole thing by -1. Then you are putting an exponent. Remember, so basically this is what this guy says is, you send me any input, I will take the e power of it and then send it out. And what this guy says is, you give me anything, I'll put a -1, multiply it and send it out. Right? This is how we compute the functions. This is how you would actually write the function if you have to write it as a program. Step by step by step. Right? And then, so then the e power exponent, and then you add a +1, and then you put the whole thing through 1 over x. So this function says, you send me anything, I take 1 over x of it, I'll send you thing out. The nice thing about this writing is it has already done the chain rule for you. Right? Because what is the x here? The x here is this whole thing. Sorry. The x here is this whole thing. It's not the x0, x1s. Right? And so basically, that's you understand this. This is the stuff that maybe people not in programming would have trouble understanding, but this is what you have done in all your life. This is a computational graph. And to compute the function, what you normally do is you throw these things, you push these things through, and you get the value. That value is 0.73. That's in the green. That's the forward pass through this graph. To compute the gradient, you go through the same graph in the backward direction. Now, when you're going in the backward direction, the thing that you need to do is you need to take, for every place, you need to take the local gradient, multiply, and then combine it with somehow, with the gradient coming down, coming back. So the inputs go forward direction, the gradients go backward direction. Right? Now the only interesting question, of course, is here when I come to 1 over x, I need to know what is the gradient for 1 over x. Thankfully that you know. And that's the minimum math you need to know. Even that you don't need to know, actually there are lookup tables, right? So how many people remember that if f of x is 1 over x, df by dx is minus 1 over x squared? That much you guys still remember. Right? So here is the thing. So you start here. In the beginning, the error basically df, the error is e, and the error differentiated to itself, with respect to itself, the gradient is 1. df by df is 1. Then you pass that through 1 over x, where x is 0.73. And then you get, and then you get minus 1 over x squared here. This number here, I'm sorry. Let's actually go through this step by step. Okay. So you have minus 1 over x squared is what you have to have here. That will become 1.37. I'm sorry, 1.37 is the input that's coming through. This 1 times minus 1 over x squared will become minus 0.53. Okay? And that is the red stuff is the gradient, the differentials that are making their way back. Okay? Okay. And then when I come here, I have the propagated gradient is minus 0.53, and then I'm adding a plus 1 to something. So that's like basically saying the function is c plus x, constant plus x. And if you differentiate, you'll get just 1, which means you multiply whatever is here by 1 and put it there. Right? That's minus 0.53. Then I have e power x. For e power x, we know that e power x differential is e power x. Okay? So then I will basically take minus 0.53 and multiply by e power x. And that will be e power minus 1, because remember, the x is the minus 1. Okay? E power minus 1 times this minus 0.53, that's minus 0.20. Okay? I'm just doing step by step here. And I continue here, I'm multiplying it by minus 1. If you ever multiply anything by minus 1, if d power d of minus x by dx is minus 1. So this minus 2.0 should become plus 2.0. Here, the gradient is being computed without you touching, because it's just going through little steps and the error is being computed. But it's not being computed in the analytical fashion, it is being computed in the numerical fashion. You just need, so in the example that I showed earlier, that guy actually had the analytical expression for the gradient and he substituted the values. Here you are just basically getting the values by composing the individual differentials. You see what I'm saying? And the only individual differential you needed are the ones of the small analytical functions that you are using. Pretty much the main big thing, by the way, the reason I'm taking this particular function is because this is a sigmoid function. It's like one of the biggest things that is actually there in the neural network. There's nothing really going on in neural networks other than weights being multiplied by the inputs, adding them up and throwing them through the sigmoid functions. Except you do them like a billion times. One after other, not billion, 250 times at least, let's say. And so it looks like a pretty complicated expression. But that's where programming is good. That's exactly where programming is good. You see what I'm saying? Okay, so you go through this. Now, the interesting thing is here there is a plus. And these are actually the places where, in fact, auto differentiation was an area looking for an application until neural networks came along. Okay? Because people have figured out how to do auto differentiation in the numerical analysis. There used to be this area called numerical analysis. People never used to care that much about it. Now they are extremely popular because essentially many of these things are. Those were the guys who used to care about continuous optimization. Those were the guys who used to care about auto differentiation. So in general, one of the things that happens is you came up to here. Up until now, the gradient is just flowing through because there is a linear path. Here you have a fork in the road. So what do? It turns, who is the guy who said when you get to the fork, take it? Some baseball guy. Anyway, so in this particular case, it turns out that what you do depends on the operation being done. The kinds of operations that will be done in neural networks are plus, multiplication, maxing, if you're doing max pooling. We haven't yet gone there, but some of you have heard of maxing. Those are the kinds of operations. And it turns out